Hi, I'm Antonio Sala, and in this video we are going to finish with the discussion on the manipulability analysis of a robotic manipulator. We spoke about the manipulability ellipsoid in units of speeds, feasible and effective speeds, given some joint speed limits. We also discussed the force ellipsoid and effective forces that could be counteracted with some torque limits in my joint actuators. And in here we'll discuss the duality between force and manipulability speed ellipsoids as a generalization of a well-known issue in, levers or gears with 1 degree of freedom. Indeed, if I have this pinion gear mechanism abstracted as cylinder rolling over a plane, then we have that linear displacement x is radius times angular displacement theta. That translates to the same ratio in speeds. But on the other hand, if I am exerting a force here that must be counteracted to avoid movement with a torque tau on my axis of rotation, then the torque tau is force times radius. Or, well, we can equivalently write that linear force is angular torque divided by rho. So linear speed multiplies by rho, linear force divides by rho. So if a gearbox has a gear ratio of 10, this means that, let's say, the fast end that moves 10 times faster can exert 10 times less force or torque. This is well known, and in our generic discussions we spoke about Jacobians, but in this case, rho is the Jacobian, so this is the particularization of these identities with the Jacobian in a generic mechanism, in which instead of having just a number as a Jacobian, which would be the gear ratio, something like that, well, in a generic mechanism like a robotic manipulator, then Jacobian is a matrix. But somehow, can we extend the interpretation that if a mechanism multiplies some speed by 10, then it divides the associated force by 10? Well, indeed, we can generalize that, and this kind of inverse relationship between linear speed and linear force regarding the gear ratio will be called duality between force and speed ellipsoids, and that will be the main goal of this video. So we just said this and this when discussing the gearbox pinion gear mechanism, and in previous videos we showed that with this equation we were able to define the velocity ellipsoid as the geometric locus of end effector speeds with unit sphere joint speeds. We needed to incorporate some scalings, whatever, but in here we will assume identity scalings because, energy conservation means that force times speed is equal to torque times angular speed in physical units, not with scaling. So the discussion in this video requires no scaling at all and defining these ellipsoids in physical non-scaled Jacobian units. So well, this is the velocity ellipsoid, manipulability ellipsoid it's called also. And then from this equation we were able to define this force ellipsoid, which is the geometric locus of the end effector forces that can be compensated with unit sphere joint torques. Then, as we can see, we have here JJ transposed, and we have here the exact same matrix but inverted. So this hints this kind of inverse relationship between speeds and forces. If speeds are multiplied by 10, forces are divided by 10. Indeed, in the force case, if Jacobian is multiplied by 10, let's say, then force must be 10 times smaller in order to keep below 1. So the Jacobian magnitude, or singular values, more on that later, will be inversely proportional to the applied end effector forces. On the other hand, as in here we have inverted, we are sort of dividing by the Jacobian, so double the Jacobian, double the speed. Then in this case, the speed magnitudes are directly proportional to the Jacobian magnitude. If we examine this with a little more depth, then if we assume that the non-scale Jacobian has this USV transposed singular value decomposition, U and V are orthogonal matrices, S is a diagonal matrix, then this is JJ transposed, and then V transposed is the inverse of V, so they cancel out, and we get this expression that, okay, it is in fact a diagonalization of a symmetric positive definite matrix, because we have a diagonal matrix S transposed and an orthogonal matrix U, so that S transposed are the eigenvalues of JJ transposed and U are the eigenvectors. So basically, if I invert this matrix, inversion changes order, but also, inverting is like transposing in U, so the end is just the same matrix, but with the diagonal stuff inverted. So then, this thing is associated to the force ellipsoid, and this thing is associated to the velocity ellipsoid. So we can see that the matrix in those ellipsoids has the same eigenvectors given by U, but eigenvalues are inverted. And in fact, as the square root of the eigenvalues are the semi-axis lengths of the ellipsoids, then the square root of S squared, let's say, because S transposed has just the squares in the diagonal, then the semi-axis lengths are given by the singular values of the Jacobian or of the Jacobian inverse. In the speed manipulability ellipsoid, semi-axis will be given by the singular values of the Jacobian, and in the force ellipsoid, semi-axis will be given by the inverse of the singular values, but the directions will be exactly the same, those given by the columns of U. So principal maneuvers have inverse magnitude, same direction. In order to better understand it, let us graphically represent what we are speaking about. I will set whatever scaling to identity. So, the matrix is JJ transposed. I called it M, and as I said, the square root of the eigenvalues are the semi-axis of the speed velocity multiplication ratio, and the inverse of this will be the semi-axis of the force ellipsoid. So with this code I drew the force ellipsoid centered at the end effector position, just for cosmetic reasons, because force is in newtons and end effector position is in meters, but it's just to have a pretty plot. And with this, I will draw the speed manipulability ellipsoid, and I am also drawing the unit circle. So well, here we have the robot pose, and then the yellow ellipse is the manipulability ellipsoid in units of meters second and effector speed, and the red ellipse is the force ellipsoid, units of newtons. And as we can see, the principal maneuvers are perpendicular columns of view. So this principal maneuver means that we can move at a very fast speed the end effector in this direction, but we can make very little force if applied in this direction, because indeed it's sort of perpendicular to the line in which the robot is almost aligned, and small force makes a great torque that cannot be compensated. So this is a maximum speed, minimum force principal maneuver. And on the other hand, we have in this direction the maximum force, minimum speed principal maneuver. The robot is almost aligned to that direction, so force in the direction of the red ellipse's major axis exert a very low torque that can be easily compensated. But on the other hand, Jacobian is almost singular, so speeds are very small. This is the kind of inverse relationship. And if we delve into the details, the SVD of the Jacobian has these principal directions in the end effector space, these principal directions in the joint torque or joint speed space, and then if the Jacobian has these principal speed ratios, then the inverse in here will be the principal, let's say, force radius. So the maneuver with smaller speed will be the maneuver with larger force, and the end effector direction will be, very large in the vertical. In the y direction, just 0.2 in the horizontal abscissa direction. And this is what we are seeing here in the figure. Of course, this was close to a singularity, but you can try any pose you wish. So in here we have another pose with the same inverse relationship between speeds in yellow and forces in red. So in summary, in physical non-scaled units, the Jacobian defines a velocity ellipsoid and a force ellipsoid which are dual, same axis direction but inverse axis length. So somehow they are two perpendicular directions that behave like a 1 degree of freedom mechanism. In my pinion gear, if I multiply angular speed by 10 to get linear speed, then I divide torque by 10 to get linear force. Then this multiply divide. In general, the singular value decomposition sort of decouples a generic Jacobian in two perpendicular gears. So for instance, the SVD and this ellipsoid duality enables interpreting a given robot pose as a kind of XY perpendicular axis mechanism with two different transmission radius, velocity of force, multiplication radius. So manipulability ellipsoid, force ellipsoid, and associated singular values and singular directions convert my robot into a kind of this XY table. So we finish our discussion with this. Thanks for watching.